Bismillahirrahmanirrahim. Assalamu alaikum students. Today we will continue with the idea of complex numbers. So first we discuss the terminology and notation. Used in the discussion of complex numbers, right? So in the last lecture we said square root of -1 is denoted by iota. We also denote square root of -1 by the letter J, particularly in physics, right? So we can write a complex number as x plus iota y, or we write it as x plus jy. Here I denotes square root of -1. In this notation, j is used to denote square root of -1. Particularly, as I said, in physics, we use letter j to represent square root of -1, because in physics, we use letter I to denote electric current. So don't get confused with the notation, whether it is x plus iota y, it is a complex number, whether it is written in this way, x plus jy, it is a complex number. Here iota is square root of -1. In this case, j is the square root of -1. So in coming lectures, we will be using this notation of a complex number, where instead of iota, we use j to denote square root of -1, right? Now, another thing, as you know, in 2 dimensions, for example, if this is x and y, it's xy plane, and we have to label a point like this point having coordinates x comma y, we often label this point with a single letter, for example, P. Even though this point exists in 2 dimensions in xy plane, so it requires 2 coordinates to locate the point, but we label this point with a single letter, say P, right? And you know, when we discuss vectors, we represent vector also by a single letter, say V. If it exists, for example, in 2 dimensions, it has 2 components, but still we represent a vector by a single letter, say V, right? Similarly, in case of complex numbers, even though we know it is actually a pair of real numbers, we use a single letter to represent a complex number. For example, we write complex number as a z, which is x plus, now I will use j, jy. So we know it is a pair of real numbers x and y, but we use a single letter z to represent a complex number, right? So we write for a complex number x plus jy z, and we know we can write it in this form. This is rectangular form. We can write it in polar form, r cos theta plus, now I'm using j instead of I, j sin theta. Then we write it as r e raised power j theta, because you know e raised power j theta is cos theta plus j sin theta. So here z is a complex number, a complex number, right? X is real part of z, real part of z, complex number z, and y is imaginary part of z, imaginary part of z, right? The quantity r is called modulus or absolute value of the complex number z, right? And theta is called the angle of z or the phase or the argument or the amplitude of z. This is the terminology which we use in discussing complex numbers. So r is modulus or absolute value of z, theta is angle of z or phase of z or argument of z or the amplitude of z. Now in symbols, we write real part of z equal to x. This denotes real part of z. We write re z. Imaginary part of z is written as imz, which is y, and mod z is written as either this way, or we simply write mod z, which is r, which is square root of x square plus y square, right? And angle of z is equal theta. So this is how we use the symbols. Re of z is real part of z, which is x. Imz means imaginary part of z, which is y. Modulus of z is written as mod z, or we use these vertical lines, is r, which is square root of x square plus y square, and angle of z is equal to theta. This was about terminology and notation. So let us move to next idea which we use. The idea is the representation of a vector by a complex number. Representation of a vector by a complex number. See what we do. Let me draw the figure. This bx, this y, this origin. Now this is z, this theta, this is a, and this is jb. Let me name it as figure 2. Let the previous figure be figure 1. So let us understand it. So in this figure 2, we take a vector z having an x component of length a and a y component of length b, right? So we take a vector z having x component of length a and a y component of length b, right? Now, if the quantities a and b are real numbers, now if the quantities a and b are real numbers, then the combination a plus jb, which we denote by z, is a complex number. Is a complex number. But in geometrical terms, let me write it. This is important. But in geometrical terms, it can be regarded as a displacement along an axis at some angle theta to the x-axis such that tan theta is equal to b by a, as is clear from figure 2, this figure. Understand it? I'm saying if I take a vector z with x component of length a and y component of length b, then this vector is shown in the figure 2. Now, if the quantities a and b are real numbers, then the combination a plus jb, which is denoted by z, is a complex number, right? But in geometrical terms, as is indicated, this complex number z is actually a displacement from origin, as is indicated in this figure 2, along a direction making angle theta with the x-axis such that tan theta is b by a, right? As is clear from this figure, if you find tan of theta, it is b by a. This is how we represent a vector by a complex number. So you can use both interpretations. So if we have a complex number a plus jb, it is actually geometrically a vector z with this interpretation, that it is making angle theta with the x-axis and its tan theta is b by a, right? Now, in this representation of a vector by a complex number, we have an automatic way of selecting out in physical problems. We have an automatic way of selecting out the physically relevant part for the purpose of analyzing simple harmonic motion, as we will discuss in coming lectures, right? If after solving, for example, an oscillatory motion problem in these terms, we obtain a final answer in the form of z equal to a plus jb, where a and b are both real numbers, then the quantity a is wanted quantity and b can be discarded, right? Now there is another important point which I want to make. Now in figure 2, we have taken a vector z having x component of length a and a y component of length b. Now we ask a question, what is jz, right? That means if I have a vector z, which is actually a complex number, and I want to figure out which vector will represent the complex number jz. So let's find out. Z is a plus jb. What is jz? Jz is ja plus j square b. Simply multiply throughout by j. So it is ja plus jjb, which is j square b, which is ja plus minus b. JA minus b. Why so? Because J square is minus 1. Remember, we are using J instead of I. J is square root of minus 1. So J square is minus 1. I replace here J square by minus 1. So I get JZ. The complex number JZ is JA plus minus B or minus B. So let us represent it by a vector. It would be like this. This is my x-axis. This is my y-axis. This is 90 degree, as you know. Let me use another color here. This is the vector JZ having y component of length A. This is JA and this is J square B. This is figure 3. This angle theta. This is JZ. This is JA. This is, let me make it clear. This is JA. And this is J square B. In other words, it is a vector having x component minus b, because J square B is minus b, and y component A. Understand it. The thing attached with J is the y component of the vector. That is A. And the thing without J represents the x component. So x component of this vector is minus b, which is just J square B, right? And y component is A, right? Compare with this figure 2. Here we had a complex number A plus JB. Thing attached with J was B, so B was its y component, and the thing without J was A, representing its x component. So it was making angle theta with x-axis. Now, what is the thing with JZ? It is making theta plus 90 degree angle with the x-axis. So what is the conclusion? Conclusion is multiplication of Z. Conclusion. Let me write it. Conclusion. Multiplication of Z, some vector representing a complex number, by J is equivalent to a 90 degree rotation. I repeat, multiplication of Z by J is equivalent to a 90 degree rotation. We had J, we had Z. This vector was shown in figure 2. Now we found JZ is a vector which is rotated through 90 degree compared to the vector z, right? So multiplication of z by j is equivalent to 90 degree rotation in counterclockwise sense or anticlockwise sense, right? So you need to remember this because it is important. Let us move to next thing. Let me change the color. My next thing is introducing the complex exponential. The last lecture and this lecture also, we used this formula e raised power j theta is equal cos theta plus j sine theta. We want to establish this result and understand this result. So let us understand it. You know, the series expansions of the sine and cosine functions is how we write the series expansion of sine and cosine function. Sine theta is equal to theta minus theta cubed over 3 factorial plus theta 5, theta raised by 5 by 5 factorial and so on. Similarly, cos theta is written as 1 minus theta square by 2 factorial plus theta raised by 4 by 4 factorial and so on. Let me name it 1 and this equation as 2. I have not used any numbers in the equations yet, right? So this is 1 and this is 2. See the pattern? Sine theta is theta minus theta cubed by 3 factorial, then plus theta raised by 5 by 5 factorial. Next term will be negative theta raised by 7 by 7 factorial and so on. So here we have only odd powers and odd factorials, and the sign of the terms is alternately changing, positive and negative. In case of cos, we have 1 minus theta square by 2 factorial, then plus theta raised by 4 by 4 factorial. Next term will be minus theta raised by 6 by 6 factorial and so on. So in case of cos, there are only even powers of theta and even powers of the factorial in the denominator, right? And you know the idea of factorial. If 3 factorial means the product of first 3 natural numbers, that is 3 into 2 into 1, which is 6. Similarly, 5 factorial is the product of first 5 natural numbers, 5 into 4 into 3 into 2 into 1 and so on. In general, n factorial is the product of first n natural numbers, right? Now let us now form the following combination. Let us now form the following combination. So we form now the following combination. Which combination? Cos theta plus j sine theta. When you do that, let me use another color. It is 1 plus j theta minus theta square by 2 factorial minus j theta cube by 3 factorial plus theta 4 by 4 factorial plus so on. Let me name it equation 3. 1 plus j theta minus theta square by 2 factorial minus j theta cube by 3 factorial plus theta 4 by 4 factorial plus so on. We have simply used this. We have written cos theta in series expansion. Then we have added to that j times sine theta. The result is this. You can check it. I can write it since, as you know, -1 is equal to j square. We can express -1 as g square. So this equation 3 can be written as, you can write it this way using j square equal to -1. You can write it this way: cos theta plus j sine theta is equal to 1 plus j theta plus j theta square by 2 factorial plus j theta cube by 3 factorial plus so on, plus you can write the nth term j theta raised power n by n factorial plus so on. I name it equation 4. 1 plus j theta plus j theta square by 2 factorial plus j theta cube by 3 factorial plus so on. Nth term can be written as j theta raised power n by n factorial. You can check it. This is same as 4. Sorry, this is same as equation 3, because in this term j square is -1, so it is minus theta square by 2 factorial. Here j cube is just minus j, so it is same as this term. So check it. Check it at home. Right? Now, the right-hand side of equation 4 has precisely the form of exponential series. You know, e raised power x is 1 plus x plus x square by 2 factorial plus x cube by 3 factorial plus so on. This is the exponential series. E raised power x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on. So this right hand side of equation 4 has the same form as the exponential series with the exponent x equal to j theta. You can see it is just if you set x equal to j theta, set x equal to j theta, what will this series look like? It will become 1 plus j theta square by 2 factorial plus j theta cube by 3 factorial. This is what it is, 1 plus j theta square by 2 factorial and so on. So I can write it as e raised power j theta. Therefore, the result is cos theta plus j sine theta is equal to e raised power j theta, right? Cos theta plus j sine theta is e raised power j theta. Let me encircle it. This is a very important result and name it as equation 5, right? This is called Eulers relation. Right? And it was set up by Leonhard Euler in 1748. So we have justified it. Now we want to give the geometrical interpretation of Euler's relation. So for that, we have to draw a diagram. We will name that figure 4. We will write geometrical interpretation of Euler's relation e raised power j theta equal to cos theta plus j sine theta. Let me underline it. Let me draw the figure. This px, this y, this origin. Now let this be point P. This is angle theta. And this point is A. And this figure is figure 4. But the last figure was figure 3. Right. Now we use the real edge. This is our real axis. Ox is real axis. Ox is real axis. And Oy is our imaginary axis. Right? Now what we do, we draw OA of length equal to cos theta. So OA is having length of cos theta. And this AP we draw of length equal to sine theta. Right? Now the vector sum OP from Pythagoras theorem will have length of 1. Its length will be 1. That's 1. Because from Pythagoras theorem, OP square is equal to OA square plus AP square cos square theta. Let me write it clearly. It's cos theta square cos square theta is written as this way also. So let me write it. This cos square theta is just cos theta whole square, right? This cos square theta, this is sine square theta. You know, cos square theta plus sine square theta is 1. So OP is 1. So the length of the vector sum of AP and OA, which is OP, is having length of 1. And it makes angle theta with the x-axis as shown, right? This is how this is represented. So you can see, if you go to the vector representation of complex numbers, now this vector OP has length 1. So it is actually, this vector is representing a complex number cos theta plus j sine theta, and cos theta is its x component, sine theta is its y component, right? So e raised power j theta, which is a complex number, is represented by a vector OP having length 1 and making angle theta with the x-axis as shown in this figure 4, right? Remember, we said if we multiply vector z by j, what happens to it? It is rotated in counterclockwise sense through 90-degree angle. Now there is a general result. What is that general result about this rotation? Let me write. More generally, the multiplication of any complex number z by e raised power j theta is describable in geometrical terms as a positive rotation through the angle theta of the vector by which z may be represented without any alteration of its length. I repeat it, the multiplication of any complex number z by ej theta is describable in geometrical terms as a positive rotation through the angle theta of the vector, by which z may be represented without any alteration of its length. That means if we have some complex number, we represent it by some vector, right? Now we multiply that complex number with ej theta. What will happen to the vector? The vector will be rotated through angle theta in counterclockwise sense, and there will be no effect on its length, right? This is the conclusion. So if we multiply some vector z by j, it rotates it through uh, this through 90-degree angle in counterclockwise sense without altering its length. But if we multiply some vector z by ej theta, it rotates it in counterclockwise sense through angle theta without altering its magnitude or length. I give this homework. Verify this result at home. This is your homework. You verify that if I multiply some complex number z by ej theta, it will be rotated through angle theta in counterclockwise sense, and there will be no effect on its length. This is all for today. Let me summarize the lecture. So first we talked about the terminology and notation. We said that we represent square root of -1 by iota or j. Particularly in physics, we use the letter j because I we reserve for electric current. Then we said we represent a complex number even though it is a pair of real numbers by a single letter z, and write it this way, where x is real part of z, y is imaginary part, r is called modulus or absolute value of z, and angle theta is called angle of z or phase or argument or amplitude of z. Then this is the symbolism. Rez means real part of z, Imz means imaginary part of z, and mod z is written this way. Then we talked about the representation of a vector by a complex number. The relationship was, if we have a vector have z having x component a and y component b, then it represents a complex number a plus jb, right? Then we said that if we multiply vector z by j, it will rotate it through 90-degree angle in counterclockwise sense without affecting its magnitude or length. Then we established Euler's formula, cos theta plus j theta, j sine theta is e j theta, and we gave its geometrical interpretation. We said e j theta is the vector. I will be represented by a vector having length 1, which is OP here, and having x component cos theta and y component sine theta. Then we said if we multiply some vector z by ej theta, it will rotate it through angle theta in counterclockwise sense without affecting its length. And I gave you homework to verify this result at home. So this is all for today. Don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.